Hi all, we're taking a look at the Achieve homework assignment for section 2.7. When I looked at the problems that I was assigned in this section, for the first one, there's really no work to show. You just need to be able to read the graph. It's asking what are the horizontal asymptotes of the function in the figure. And remember, horizontal asymptotes are just the y values that the function is going to approach as x approaches infinity or as x approaches negative infinity. So I can see in this problem up here, as x is approaching positive infinity, as the x values get large, it appears that the y values are going to level off to the horizontal line y equals 1. That's what you would have to assume by the graph given. So you'll see the upper asymptote equation is y equals 1. And then for the lower asymptote equation, for the lower horizontal asymptote, typically we only have one horizontal asymptote in a problem. This one does have two, since the horizontal asymptote to the right is not the horizontal asymptote to the left. You would say as x goes off to the left, as x approaches negative infinity, what one y value does it seem to approach? And it seems like as x approaches negative infinity, the y values are going to approach -3 from values beneath -3. Well, that's still going to leave us a horizontal asymptote of y equals -3. So you can see that's what I put for the second part there. For number 2, similarly, there really wasn't any work to show. I just put the answer on my sheet here. And the reason for that is because it's the limit as x approaches infinity of the rational function 13x over 14x minus 6. And the limit as x approaches infinity, you'd do the exact same thing as if I were asking you to find the horizontal asymptotes. Anytime in a rational function, when the degree of the numerator and denominator is the same, we say your horizontal asymptote is going to be at y equals the fraction of the leading coefficients, which in this case is 13 over 14. But you can literally think of that. If you plug in some enormously large number in for x in the numerator and in for x in the denominator, then that 6 becomes irrelevant. If that's 14 trillion minus 6, well, you might as well just be calling it 14 trillion. The minus 6 becomes irrelevant. So the only thing that's relevant is the ratio of the coefficient of x in the numerator and the coefficient of x in the denominator to get that final answer of 13/14. For number 3 here. Again, really no work to show. Why is there no work to show? Well, because it's a limit as x approaches infinity. Every single solitary time, if the degree of the denominator exceeds that of the numerator, y equals 0 is always your answer. Similarly, you'll see I didn't show any work for my number 4, so it's probably obviously quick. Yep, number 4 is just like number 2. We have a limit as x approaches infinity of a rational function whose numerator and denominator have the same degree. Every single solitary time that's the case, the limiting value is going to be the fraction of the leading coefficients, 10 over 9 in this case. For number 5. So, we have a limit as x approaches negative infinity of 4x squared minus 5 divided by 8x plus 3. Okay, so here's the work I showed out in that one. I knew that the limit was either going to be going to infinity or negative infinity, since the degree of the numerator exceeds that of the denominator. In order to show my work in this problem, what I did to simplify it out is I divided, and this is the thing you should always do. If you want to simplify a rational function inside of a limit, just divide by the degree of x in the denominator into every single term. So I'm going to divide every single term in this fraction by x to the first. That's a legitimate algebraic maneuver. Okay, so when I do that, this is going to give me the limit as x approaches infinity. I'll have 4x to the first minus 5 over x. And then my denominator is going to be 8 plus 3 over x. Okay, now from this step to this step, I allow x to go to negative infinity. Well, you know 5 divided by either negative or positive infinity, that's going to go to 0. Same thing with a 3. So those two become completely, utterly irrelevant. So what's the rest of it? You would have 4 times a number approaching negative infinity divided by 8. So essentially you have 1/2 of negative infinity. 1/2 of negative infinity, still negative infinity. Thus, that's the answer for number 5. Now you're thinking, well, hey, these problems aren't bad at all. They're really not. Number 6 is similar. You'll see the work I did again. I have a limit as x approaches negative infinity. I went through inside the rational function and divided by the the degree of x in the denominator. So I divided everything by x to the first. When I do that and simplify, I get 5x squared minus 2 over x divided by 9 plus 8 over x. Now, from this step to this step, I took the limit as x approaches negative infinity. Any finite number divided by an infinite number, whether positive or negative, goes to 0. So those two go to 0, become irrelevant. So now what's the rest going to be? You're going to have 5 times a number approaching negative infinity squared. Well, that's going to be a number approaching negative infinity squared is going to be a number approaching positive infinity. So you have 5/9 times positive infinity, which is positive infinity. We're positive of that. For number 7, it goes back and actually you'll see it took me 2 attempts to get this one. And the reason is I was thinking it was like the earlier problems where it was just asking me the limiting value. You'll see I put 11 over 10 for my answer. This one is specifically wanting the horizontal asymptotes. Yes, as x approaches infinity of this rational function, you just say, well, you just have to take the fraction of leading coefficients, 11 over 10. But this is wanting the horizontal asymptote. That horizontal asymptote is y is equal to 11 over 10. So please make sure you put the equation there. And I should have known because it specifically says equations. Number 8. Again, it's wanting an equation. Or there wasn't any work to show why. Because every single solitary time, if you're trying to find the limit, or in this case, the horizontal asymptote, which is the limit as x approaches infinity, but if you're trying to find it where the degree of the denominator exceeds that of the numerator, then as x goes to infinity, you know that the y value is going to go towards 0. So yes, the limit as x approaches infinity is 0. Yes, the horizontal asymptote is also the equation y equals 0. Number 9. And gorgeous. This one, a little bit more troubling because it's not a rational function. You don't have a polynomial divided by a polynomial, but it's still not hard to think about. So I had my f of t is equal to 9e to the t divided by 2 minus e to the negative t. Well, I know that e to the negative t, that's 1 over e to the t as a term in the denominator. I'd rather not have any negative exponents in my expression, so I'm going to multiply by e to the t over e to the t. Remember, that's just multiplying by an understood 1. Now, when I multiply by that understood 1, though, this makes it more clear. I'll have a 9e to the 2t divided by 2e to the t minus 1. Now, when I'm thinking about this, I can say, well, I know there's not going to be a horizontal asymptote. Why do I know there's not going to be a horizontal asymptote? For the very same reason in a rational function, anytime the degree of the numerator exceeds that of the denominator, there's not any one y value it's approaching because it's going to go off towards infinity. In the same manner here, your exponent or your exponential term in the numerator is always going to be a greater power than the exponential term in the denominator. So this is going to go off towards infinity as t approaches infinity. That's what I put here. No horizontal asymptote since the degree of the numerator exceeds that of the degree of the denominator as x approaches infinity. Now, it was asking for any horizontal asymptote. So notice, and I should have said t here. So as t approaches infinity, yes, this function is going to go down. But what about as t, or I put x here, approaches negative infinity. Well, as the function approaches negative infinity, I know that any exponential function is going to get ridiculously small. Think about the graph of y equals e to the x. It asymptotically approaches 0 to the left. Well, e to the 2t is going to approach 0 as t approaches negative infinity. So I can say, well, my numerator is going to be 9 times 0, which is 0. Your denominator would be 2 times the number approaching 0, but then you'd still have this minus 1. So you'd say, well, 0 divided by negative 1 is 0. So as the values approach negative infinity, whether you want to call it x or, as I should have called it, t, the y values are going to approach 0 as they move towards negative infinity. So this is one of those cases similar to the first drawing, where you have two different horizontal, well, I shouldn't say horizontal asymptotes. You have a horizontal asymptote to the left, and to the right, it's just approaching infinity. So you can say the only equation of the horizontal asymptote is y equals 0. Pretty cool problem. Speaking of pretty cool problems, I like this next one. We have the limit as x approaches infinity of the root of 3x to the fourth plus 2x plus 4 over 2x cubed plus 7. There's no work to show here. Why is there no work to show here? Well, because if I say, guys, what's the degree of the denominator? It's degree 3. If I say, what's the degree of the numerator? Please be careful. Don't tell me it's degree 4. That x to the fourth is inside of a square root. So the numerator is degree 2. So you'd say, okay, what do we know about any time you have a limit going to infinity of a fraction whose numerator is of lower degree than the denominator? It's going off to 0. Because as x gets large, that denominator is going to get large, infinitely times larger than the numerator will. So I can say, all right, since this problem is going to have a larger denominator than numerator, infinitely times larger, this fraction is going to go off towards 0. And again, if you're saying, but why? Why? Every single time the degree of the numerator, or I put here, since denominator degree of 3 is greater than the numerator degree of 2, every single time the degree of the denominator exceeds that of the numerator, if you've got a limit going to infinity, then your fraction's going to 0 every single time. No work to show. For number 11, I'm looking at that one and saying, well, do I need to show work on this one? Well, yes and no. I know it's not going to be 0. How do I know it's not going to be 0? Because look at the degree of your numerator. It's degree 2. What's the degree of your denominator? Oh, square root of x to the fourth. It's also degree 2. So I'm going to show out my work on this one. I know it's not simply 0, and I know that there is a horizontal asymptote. So here's how I do that. I go through and I say, well, all right, since I have that square root of x to the fourth in the denominator, I'm going to go through and divide by an x to the fourth inside of both of those terms inside the root. Now, divide by that exact same term in the numerator. And you might look at this and say, you're not dividing by the same term. Yes, I am. The square root of x to the fourth is x squared. A lot of students get confused right here. They'll think that I'm not doing the same thing. I absolutely am doing the same thing. The square root of x to the fourth is x squared. So I divide both terms in the numerator that are not inside of a square root by x squared whenever I divide the denominator by the square root of x to the fourth. Now, when I simplify, I'll have the square root of 64 plus 5 over x to the fourth. My numerator is going to simplify to just be 16 plus 7 over x to the 5/3. Now, this term and this term become irrelevant. As x goes to negative infinity, that term goes to 0, that term goes to 0. So then you're just left with 16 over the root of 64, which we know the root of 64 is 8. 16 over 8, 2. Now, this one, it's just wanting the answer to, as opposed to some of them where they wanted the equation of the horizontal asymptote. So please don't put y equals 2 there. Just put the answer to. For number 12, we have the limit as t approaches infinity of t to the 4/3 plus 7t to the 1/3 divided by 4t to the 2/3 plus 13 squared. I could see some people getting tricked on this one. If I say, hey guys, what's the degree of the numerator? Hopefully you'd say, well, it's the 4/3 because that's the highest power of t in the numerator. What's the degree of t in the denominator? And you would say, well, before I determine that degree, I'd have to understand its power to a power. 2/3 times 2, hey, that's degree 4/3 as well. So t is to the 4/3 power in both the numerator and the denominator. So I need to go through and simplify this expression. What do? I'm going to go inside of this group squared in the denominator and divide by the power of t inside of that group. Inside of that group, it's t to the 2/3 that I'm dividing each of those terms by. Please understand though, when you're dividing by t to the 2/3 inside of a group squared, you're really dividing by t to the 4/3, which is precisely what I must do in the numerator since it's not inside of a group squared. So in the numerator, I divide by t to the 4/3 in both terms. Now, when I do that, it's going to simplify out my first term to be 1. My second term is going to be 7 over t to the first. In my denominator, I'll have 4 plus 13 over t to the 2/3. The 7 over t and the 13 over t to the 2/3, as t goes to infinity, those fractions go to 0. So then we're just left with 1 over 4 plus 0 squared. That's 1 over 4 squared for 1/16. Gorgeous stuff. Moving on down through here, number 13. Absolute values. So whenever you deal with absolute values, you need to think about whether the limit is approaching infinity or negative infinity. So I can't leave that absolute value in my problem. But what I understand is that the absolute value of x, it's either x or it's negative x. For values of x that are negative, the absolute value just acts as the negative of the function. That's all I've done here. I said, since I'm going off towards negative infinity, that absolute value of x is always going to act as the negative of x. Like if I say, hey guys, what's the absolute value of -5? You'd say 5. Why? Because you know the absolute value is going to change the sign and make it positive. The only way that it can change the sign is if it's the negative of the function anytime x is negative. So I go over and I simplify and I say, well, my numerator, as x approaches negative infinity, that numerator is the same thing as negative x minus 2x. Now, I've left the denominator alone. I can say, well, then my numerator is negative 3x over x plus 2. I can see that the degree of the numerator and denominator is the same. I could already look at this and just say, John, your answer is going to be negative 3 over 1, or just negative 3, done. But now, just in order to show the work in this problem, you could say, well, you could go ahead and divide by the degree of x in the denominator, divide every term by x, and now whenever you do that, you can see, well, okay, your numerator is going to simplify to be negative 3. Your denominator is going to simplify to be 1 plus 2 over infinity. That's just going to be 1 plus 0. So I get negative 3 over 1 as I take that limit to negative infinity. And you can say, final answer, negative 3. For number 14, I like it a lot. Let me go back to here. There we go. 14. When we look at this one here together, guys, we start off with an expression, limit as x approaches infinity, of the root of x to the 4th plus 3x minus x squared. So you say, well, essentially, it's the square root of infinity to the 4th minus infinity squared. Seems like it would be 0, but you don't want to make that conclusion without showing it. So here's what I'm going to do. I'm going to go ahead and try to simplify this expression. How do I simplify it? The way I simplify any binomial expression with a root in it is to multiply by its root conjugate, which is the same two terms with the opposite sign in between. Now, if I do that to this function, you can't just multiply by it. because then you're changing the value. So you must also divide by that same quantity. So I'll say, okay, now why am I multiplying by this? Because now when I do so, I can say, well, anytime you multiply by the conjugate, it's just the first term squared, which is just going to be the group x to the fourth plus 3x to the first power, and then minus the second term squared, negative x squared times an x squared, that's going to be net minus x to the fourth. Now, I went ahead, simplified this out. Your x to the fourth cancel each other out in the numerator, and we're left with the expression. This is just the limit as x approaches infinity of 3x divided by all this denominator. Now, how did I know that the answer is 0? There's no more work to show. Why? Because anytime you're inside of an infinite limit, if the degree of the denominator exceeds that of the numerator, your answer is 0. Period. End of story. So I can say, yep, numerator's degree 1, denominator's degree 2, whether I'm looking at this term or this term, they're both degree 2. So since the denominator degree is greater than the degree of the numerator, answer 0. That will always be the case in an infinite limit. Now, for the next problem here for 15, we are looking at the limit as x approaches infinity of 3 root of x minus the square root of x plus 5. So similar to the last problem in that it's a conjugate expression, and I can't just plug the infinity in because you'd get infinity minus a number approaching infinity. So, I don't know. In order to determine that out, and instead of just saying, I don't know, you multiply by the conjugate. So I take the exact same two terms with the opposite sign in between, multiply it by it. Of course, I have to divide by that term as well. In the numerator, I simplify. 3 root of x times 3 root of x is 9x to the first. The square root of x plus 5 times the square root of x plus 5 is the group x plus 5, but it's that entire group being subtracted. Please be careful. I could see a lot of people not putting the parenthesis sign there, and it would be bad. You're subtracting the entire group x plus 5. Now, in my numerator, 9x minus x will give me 8x minus 5. My denominator, I've just left the same since this step. Now I'm looking at it and saying, okay, look at the degree of x in the numerator. It's degree 1. What is the degree of x in the denominator? Whether it's this term or this term, those are both degree 1/2. Every single solitary time, if you're inside of an infinite limit, if the numerator is greater degree than the denominator, then that fraction is going off towards infinity. Now, it is positive infinity too, because you can see your numerator is going to be positive in sign and your denominator is going to be positive in sign. Positive over positive means this is going to positive infinity. And again, that's always going to be the case anytime the degree of the numerator exceeds that of the denominator. Next one, I could see some people struggling with it, but it actually ends up being a very easy problem if you remember your property of logarithms. So we have the limit as x approaches infinity of the natural log of 2x plus 1 minus the natural log of 7x plus 1. So I can say, well, what am I supposed to remember here? The rules of condensing. Anytime you have logarithmic expressions that are separated by a minus sign, you can combine them, and the one that's positive has a factor in the numerator. The one that's negative has a factor in the denominator. So this is equivalent to the limit as x approaches infinity of the natural log of 2x plus 1 over 7x plus 1. And then I can say, well, notice the degree of the numerator and denominator are the same. So as x goes to infinity, what does this expression approach? It approaches the fraction of the leading coefficients, 2 over 7, which you'll see is my final answer, the natural log of 2/7. And finally, number 17 here, the work I did for that one, we had the inverse tangent of 1 plus x over 1 minus x, and we were trying to find the limit as x approaches infinity. Well, the first part, really easy, and I showed out work. You really wouldn't even have to show this step. You could just say, John, the degree of the numerator and denominator is the same. So why don't you just take the fraction of the leading coefficients in the inside and say that this is going to approach the inverse tangent of 1 over -1. the inverse tangent of -1, and get your negative pi over 4 there. You could do that. Woo, and that would be gorgeous. I went ahead and showed out the algebraic step and saying, well, let's divide by the degree of x in the denominator, which is just x to the first. I divided every single time by a term by x to the first. I know this term and this term are going to go to 0 as x approaches infinity. That does leave you with the inverse tangent of 1 over -1. Please notice from this step to this step, the limit is dropped. Why? Because I literally allowed x to go to infinity. That's why this term is ignored. That's why this term is ignored. 1 over infinity, it's 0. So I can say, well, okay, those cancel out and just become a 0. So we have the inverse tangent of -1. And then you're supposed to remember, I always think of it in terms of the unit circle. When is the inverse tangent -1? Well, at the part where quadrant 4 splits, sorry, I should say at the midpoint of quadrant 4, it'd be 7 pi over 4 on your unit circle, but you can't say 7 pi over 4 because the range restriction for the inverse tangent function is between -pi over 2 and pi over 2. So you say, well, the coterminal angle there to 7 pi over 4 is our -pi over 4 answer for the inverse tangent. And fortunately, it does want you to give the nice exact answer as opposed to trying to go to your calculator and getting a wimpy decimal approximation for that. You shouldn't need a calculator for inverse tangent. Okay, guys, so that does it for this section. Please let me know if you need any help. I'll be glad to help wherever I can.